I'll keep this short because we're coming close to lunch. I'll just cut it in half because honestly, all I really wanted to do was to answer that difficult question of, so what do you do, Cormac, when you're not teaching? We hear all about this research. What do you actually do? Well, the answer is I'm now what's called a historian of science, I suppose. What a historian does is we look at things like theory and models and how do models develop. So I'm sure you've all heard the analogy, a research scientist is very like a research scientist is very like a detective in many ways, the way they piece together evidence and draw together a theory. Well, in that case, I'm more like the super cop. Our group is like, those of you who are fans of the TV series will know Line of Duty, where this kind of AC-12, much feared unit comes into a police station and asks questions. Yes, but why did you follow this line of inquiry and not follow that line of inquiry? Why did it take 3 years for this evidence to emerge when it was sitting there all along? And that's really what we do. And, it's a wonderful teaching tool as well, because I find for myself in the first place, to understand a lot of modern physics, my area is 20th century physics, I very often needed to know anyway. I needed to know how did we get to that point? That sort of get over it, here it is, just doesn't work in something like general relativity. You really have to have some idea of how it came about. It's just too hard otherwise. And then I found that students found the same thing. So it's also a very interesting teaching tool. But it turned out when it comes to writing research papers, it's a much more muscular field than you'd think. It's not a sort of a genteel hobby. There are extremely bitter battles in the history of science about who discovered what and when it was first discovered, etc. So anyway, we won't talk too much. It's just to give you a flavour. But for example, for the purposes of today, we'll refer to the team as AC-12 because it's the same idea. It's a unit like that. So AC-12 would want to know immediately, first of all, what is this Big Bang model? And we'll cut to the chase and say, basically, it's the model that the universe was once super dense and super hot and has been expanding and cooling over time. Note that it doesn't say anything about origins. None of the Big Bang scientists ever claimed that it did. That's a very important thing. But the sort of evidence we would look at and sift through would be, where did the evidence first emerge? And the sort of four basic planks of evidence would be the runaway galaxies, of course, the recession of the galaxies, the abundance of the chemical elements, the distribution of the galaxies, and the background radiation. And we'll have exactly one sentence on each of those. But of course, the big problem from the point of view of pedagogy is in terms of the difference between science and, say, crime is in science, your narrative is usually embedded in some sort of theory. And unfortunately, theories of the universe are embedded in the theory of gravity. And the modern theory of gravity is Einstein's general theory of relativity, which is not very friendly. There's no question about it. It's mathematically very dense. So that's why we don't really teach it even at undergraduate level in college. Very few people are lucky enough to do modules in cosmology because it's embedded not even in the special theory but in the general theory of relativity. But anyway, to answer the question of what does a historian do is we review how models develop, and we also very often consider roads not taken. And as you'll see in the last slide, it's surprisingly contemporary. Very often a question today has echoes going way back to the beginning of modern cosmology 100 years ago. It's surprisingly useful. Okay, so I'll just point out again, the AC-12 team, the first piece of evidence they would look at is, of course, in 1929, Hubble's great discovery that the galaxies seemed to be moving away, and not only moving away, but moving away at a speed proportional to a distance. Now, any physicist in the room and any historian would, of course, want to know is, how do you measure that? How do you know that? And the first part is easy enough. Surprisingly enough, the motion of the galaxies is easy because you can simply measure the motion of stars by using Doppler effect. By looking at the spectrum of well-known stars, you can see by the fact that that spectrum is redshifted that they're moving away. So that was known from about 1915 onwards. What was much more difficult was to know the distance of the galaxies, and it's exactly the problem PJ was talking about earlier. How do you know if something quite far away, how do you know if it's relatively small and close or extremely large and far away? And in fact, philosophers talked about this for years until they discovered there's certain types of stars, like Cepheid variables, where we know what their intrinsic luminosity is from basic physics, from the way they pulse. And therefore, if you know what its intrinsic luminosity is, and then you look through a telescope, you compare what it should be to what you see, and that tells you how far away it is. So this was Hubble's big discovery using the world's largest telescope. He was able to work out just how far away these galaxies are, and therefore he was able to work out his famous Hubble's law. Anyway, in terms of the narrative, that was very upsetting. This is around the 1920s for a lot of physicists because, of course, according to PJ again, Newton's law tells us that things things pull together, they don't push out. So what was pushing these things out? How can the galaxies be receding? And the bad news is the only explanation is in the modern theory of gravity, which is Einstein's theory of relativity, which states that space and time aren't fixed at all, but form an entity called space-time. And space-time itself isn't absolute. Instead, what happens is if we take a region, and it's actually easier than people think, if we take just a region of space, the geometry of that region is effectively dictated by the matter within it. In simple language, the sun doesn't actually pull the Earth in some invisible tow line around. That's not how it works at all. What happens is the sheer mass of the sun distorts the space around it, and the poor little Earth is just running through the space there. The Earth thinks it's going in a straight line. It's because the space it's moving through is distorted by the mass of the sun. That's really what the theory of relativity is. But of course, if you apply that to the universe as a whole, you get some strange results. It was the mathematician Alexander Friedmann who first pointed out that relativity predicts that a universe couldn't be static. It either expands or it contracts, but nobody paid any attention. Similarly, Belgian priest Georges Lemaitre also suggested something similar, but even was able to tie it to emerging results, the early results of Hubble. And again, the sort of thing I look at is nobody paid attention to either of these two guys at the time. In fact, they were roundly ignored, and the only person who read their papers, Einstein, completely dismissed them. And so the sort of question we ask is, why is that? And we write long papers about that. But anyway, the paradigm shift then happens a few months after Hubble's law was 1929. In 1930, the sort of community wakes up and begins to realize that actually, if this is really true, if this is motion, velocity versus distance for the galaxies, it must be that it just can't be explained in terms of Newton. It must be that what's really happening, of course, is the galaxies aren't moving anywhere. This is the first evidence that space is in fact expanding as relativity would predict. And at that point, Friedmann models would be accepted. And the sort of thing our unit would look at is, why is that? And the answer is, of course, because the evidence is there now. Now the evidence is pretty clear, and that's what usually happens, as Thomas Kuhn always pointed out. There's a point where the previous theories just break down. You can't really hang on to Newtonian gravity anymore in the face of something like this. Okay, oh yeah, I just mentioned this was our first little success, by the way. I became interested in Einstein's First. What did Einstein first do when he heard this, when he knew the new evidence was in? And the answer is he had a fairly obscure model, his first model of the expanding universe, which had never been translated. So myself and a colleague here, Brendan McCann, in WIT, we got together and we translated the paper. And to the victors go the spoils, because no sooner had we translated that, we found that, oddly enough, the whole point of this paper was to extract parameters like the density of matter, the time span of expansion, the cosmic radius. And there was a factor of 10 wrong in all of those, which was really interesting because nobody had never noticed it before, presumably because it had never been available in English before. So that was our first little triumph. But not only that, and this is where it gets, the fun part is, not only has Einstein got a systematic error in all of his little calculations, but it's not that clear in the paper where the error is. And somebody contacted me from Oxford to say that they had this blackboard, and sure enough, on the blackboard are the main equations of that paper. But the real bonus is there's an extra line on the blackboard. It's actually this one here. It's an extra line in the blackboard which tells you exactly what Einstein's mistake is. So just like a student, you can see, aha, gotcha. You can see immediately that's what his mistake was. So that was really nice, and we got that was my first, if you like, we made the front cover of the standard European journal on the history of physics, which I was very pleased about, so that was great. Anyway, we're getting back to the Big Bang. This is the second part of the talk already, and getting back to the Big Bang, it was, of course, Georges Lemaitre who first said, well, if you have something that's expanding now, presumably in the past it was smaller, and if we simply keep going and keep rewinding, does that not mean the universe was once extremely dense and extremely hot? And in fact, Lemaitre went even further and said, did it have a beginning which was explosive at sort of time zero? And again, the sort of thing that my team is very interested in is, was that accepted at the time? And the answer is no, not at all. Don't get confused. The expanding universe was inevitable. People had to accept that. But this business here, everybody just thought it was ridiculous. And I think that's right because, again, scientists like detectives, slim enough grounds. You're talking about a recession of galaxies. To start talking about a universe billions of years ago with some sort of fiery origins based on that, you've only one piece of evidence, so the grounds are slim. Instead, what happened was a second piece of evidence emerged in the 40s. This is one of my favorite guys in 20th century science, George Gamow, a maverick emigre Russian scientist, and he was the first to point out that the old story of the elements being formed in the stars isn't actually true. It's true for some of the heavy elements, but it's not true for the light elements. There's no way you can explain the abundance of hydrogen and helium, in particular in terms of stellar physics. And he was the first to say, maybe if we take this mad infant universe of Lemaitre, maybe if we take this infant universe, maybe that's where hydrogen and helium got formed. And he was able to show that actually, yes, the predictions match exactly. We do live in a universe that's pretty much 3/4 hydrogen by mass and 1/4 helium. That is the main proportions of our universe. And he was able to show you can only get that by assuming the universe was once extremely small and extremely hot. So that was the second plank of interest. Not everybody paid attention, but they also made a third prediction, which is actually, if that's really true, without going into detail, if that's really true, if the universe was once small and hot, there should actually be some radiation left over. This is the famous cosmic background radiation. And again, the sort of thing we get really excited about in our group is we then ask, well, why didn't anybody go looking for it? And there's all sorts of social reasons for that, actually, mainly because there were 3 Russian scientists working in America in the 50s when sort of anti-Russian sentiment was at its height, and I think that's probably the main reason. But anyway, long story short, these guys made a very important prediction, and nobody looked for it. Instead, along came something most of you will have heard of, a completely rival model by a very, respectable group in Cambridge led by Fred Hoyle. And what Fred Hoyle suggested was you could have an expanding universe, but it doesn't have to start with a big bang. It could be it's always the same because there's a certain amount of matter created all the time, which sounds a bit crazy until you realize the amount of matter you need is very, very small. So this is a perfectly reasonable idea at the time. You might say, why did it take to the 1950s for this to emerge? And we'll come back to that. But it's a very, and he got the idea from this famous film. But anyway, the idea was this was a rival thing, which a lot of people, particularly in the UK, actually jumped on. And then for the decade between 1950 and 1965, there was a rather bitter and unpleasant debate between the steady staters and the big bangers. So Fred Hoyle here and his team felt that they were on the right track, whereas this chap here, Martin Ryle, decided if you got a big enough telescope and you looked at galaxies, say 1 million years ago, and then 10 million years ago, and then 100 million years ago, that'll tell you, because if they're different, then we live in a Big Bang universe. If they're the same, then we live in a steady state universe. Quite simple. And again, the sort of thing we like is actually, they did show long before, I'm going to talk about the famous discovery you all know about, but long before the background radiation showed up, that was really the end of the steady state model. Radio astronomy in Cambridge had shown that actually the distribution of the galaxies over time is completely different, which is not what you get in a steady state universe. But anyway, you may have heard of this as a bonus, not the same team, but using the same technique a crowd in America discovered by accident, literally tripped over it, the cosmic background radiation. They were looking for one thing, they had this huge receiver, and what did they find but this ubiquitous signal all over of very, very low frequency. They had no idea what it was, but when they consulted people who did know something about cosmology, everybody realized that this was the famous background radiation, literally an echo of the Big Bang. And that's what people study today in cosmology. That's how we know, or what we think we know about the early universe. Everything comes from this stuff, looking at this background radiation. And just a couple of things. First, this is our second little triumph. This launched us as a little group, because what happened was when I was looking into the history of this stuff, what did I discover? But in fact, Einstein himself, 20 years before Hoyle, Einstein had attempted the idea of a steady state universe. And I was really pleased when I discovered this, because in fact I had always wondered about that. I mean, why did it take from 1930 to 1950 for someone to say, well, you could have an expanding universe where it is in a steady state? And I was really pleased to discover a manuscript by Einstein in plain sight on the main Einstein webpage in his own handwriting, where he attempts a steady state model 20 years before Hoyle. But the interesting thing is he never published it because he wasn't convinced by it. He felt that, clearly in his own notes afterwards, he felt that the idea of matter being created continuously was a bit far-fetched. So we got a lot of attention. If you had told me 10 years ago we'd make the front page of Nature and various things, I wouldn't have believed you, but that was our sort of claim to fame, that we discovered this. I suppose the truth is, I speak a little bit of German, and Brendan speaks a lot of German. You had to be able to speak German, you had to be able to read Einstein's handwriting, and you had to know enough mathematics to understand what he was talking about. Presumably that's how it was missed all along. It was misfiled as something else. But it is kind of got me interested that there's still things in history out there to be found, no question about it. Anyway, so from the point of view of AC12, if we were to sit down and say, well, how's this inquiry going? We would say, yeah, well, the Boffins seem to have it about right. There are 4 planks of evidence that measure up: the expansion of the universe, the abundance of hydrogen and helium, the distribution of the galaxies, the cosmic background radiation. All of these are well established now. So when you pick up a magazine today, you'll probably see nothing but, speculation about multiverses and inflation and God knows what else. And I think journalists sometimes forget to say, yeah, but the basics are actually very well established. And so, yeah, literally 2 or 3 more slides. I'll just say today, what do people do in Big Bang cosmology? What they mainly do is they study this the spectrum of this background radiation. They look at this in ever increasing accuracy using ever more expensive satellites. And anyway, as some of you will know, the bad news is to make sense of the Big Bang model nowadays, the more we look at it in detail, the more we find that actually, as well as ordinary matter, to explain how the universe works, we need two other hypotheses. We need the hypothesis of dark matter, which is about 22% of what matter energy seems to be made up, and something else. Dark matter, of course, being matter that you can't see but has a gravitational effect, and dark energy, which is even worse, which is something that nobody knows what it is, and yet it seems to be causing the push out. Again, where we come into this sort of thing, the historian has something to add there, because when you look at the history of dark matter and dark energy, you find that contrary to what people seem to think, they're not modern at all. In fact, those ideas go right back to the early days of cosmology. So I'll just show you that. Oh yeah, I've just mentioned what is dark matter. It's matter where it has a gravitational effect on something, but you can't see it through a telescope. It's not actually that crazy an idea. Nobody ever said that the gravitational interaction has to have some link with the electromagnetic. It's perfectly possible you could have matter that can't be seen. What's much more weird is this one here, this dark energy business. As they measured galaxies in the modern era, they discovered not only are they moving away, but they're actually accelerating. And that led to the idea that something, even in relativity, we need an extra force that's actually pushing them out faster and faster. But what a lot of people don't know is actually Einstein predicted that in 1917. Back in 1917, he was already talking about the cosmic energy of the vacuum, that the vacuum would have its own energy. So there's a lovely point out there. Yeah, there's a lovely intersection there of, history is never dead, especially history of 20th century physics. There's a lovely intersection of history with today's science. The basic big three problems in cosmology today are the nature of dark energy, the nature of dark matter, and the singularity problem. But every single one of those are actually things that were asked about in the 20s and in the 30s. So I must say I'm very pleased that I would never have managed this as a physicist, but as a historian I get conversations and emails all the time from leading people in cosmology all the time, because they often want to know whether Einstein or Friedman, or is there any evidence so-and-so thought of this in the 1920s. And I often get queries like that, and a lot of the time I can answer, yes, actually they did. All it takes is somebody to have the time to look through the manuscripts. A lot of the time now we have handwritten notes from these people, and that's basically what my group does. Okay, so just to finish, if anybody wants to know any more, first of all, that thing about the blackboard, there's a nice description of that just last June. I only saw it this morning, but in Physics World of last June, there's a lovely article on Einstein in Oxford, and actually mentions our discovery of the blackboard and all that. And then in terms of the steady state model that we discovered, again, Physics World had a sort of editorial thing on that quite a while ago in September 2014. Okay, so I'll leave it at that. Enjoy your lunch, everyone.